So one of maybe the most famous applications of a lot of the things we've been thinking about is the technique of least squares approximations. So let's start with a motivating example here. So a very classical example of this theory is the theory of fitting a line to data. So in this example, I'm looking at a collection of 3 data points in the plane. And what I want to do is I want to fit a line to this data. So my line has equation given by f of t equals a0 plus a1 times t. So the idea is that the graph of this function is some line, and I want to choose the coefficients a0 and a1 in such a way that this line passes through all of the points. Now I know what you're thinking. You're thinking, well, I'm looking at these points and I see that's not going to happen. That's not going to work. And you're right. And the reason you're able to see that so quickly is because you're a human. Your brain is designed to think sort of geometrically in that way. But a computer does not think that way. A computer looks at this problem and says, okay, how could I get started? And the way a computer would get started is the computer would say, okay, well, if this line exists and it does pass through all these points, what does that actually mean? Well, the first thing it means is that if we look at the first data point, which has coordinates 0 and 2, we should be able to plug in t equals 0 into the formula for the line, and the output should equal 2. Well, the formula for our line is a0 plus a1 times t, so this should give us the equation a0 plus 0 times a1 equals 2. This is one equation, and we can represent this equation as one row of an augmented matrix. Again, the equation here is a0 plus 0 times a1 equals 2. So we have an augmented matrix here, where in the coefficient matrix, we have labels given by a0 and a1, and the coefficients are 1 and 0, and we're augmenting with 2 here. What would it mean for our hypothetical line to pass through our second data point here? Well, this would mean that, so the second data point here is 3, 1. So this would mean that f of 3 would equal 1. The equation that pops out of this says that a0 plus 3 times a1 must equal 1. And I can add that equation into my augmented matrix. And finally, what would it mean for our line to pass through this third data point here, 1, 0? Well, that means that if I plug in 1 into my line, I produce the number 0, which gives me the equation a0 plus a1 equals 0, and I can put that equation into my augmented matrix. So now I have a system of equations represented by an augmented matrix. If I'm a computer, what do I do to solve the equation? I row reduce. And when I row reduced, I got this reduced row echelon form. I found 2 pivots to the left of the augmented column, so 2 pivots in the coefficient matrix, but then I found a pivot in the augmented column. This system is inconsistent. Now, as humans, we knew the system would be inconsistent because we knew there was no line that would pass through all 3 of these data points. But a computer would have to go through this process to make that conclusion on its own. Now, I want you to think carefully about all the things we've learned in this course and how a lot of the language we've developed is useful in thinking about this problem. What are we saying here when we say that this system is inconsistent? Well, the system is described by a coefficient matrix A augmented with some vector 2, 1, 0. The reason this system is inconsistent from our point of view is that the vector 2, 1, 0, which maybe I'm calling vector B here, is not in the column space of A. That's the fundamental problem, is that by studying this problem, we end up studying an inconsistent system, and the reason the system is inconsistent is because this vector B, 2, 1, 0, is not in the appropriate space. It's not in the column space. Now, I want to point out that this kind of thing happens all of the time. In the so-called real world, think about how people work with numbers. It is extremely common for people to work with numbers that are, or data generally, that's collected with imprecise methods. Maybe a biologist is out in the field making some sort of measurements, and when a person makes measurements, they're necessarily incorporating some sort of error into their technique, whether it be imprecision in the instruments they're using to make the measurements, or rounding errors when they have to make a decision what the actual measurement is. Think of a chemist who is maybe weighing out certain chemicals or trying to measure the mass of certain chemicals. When you're doing that, when a chemist is doing something like that, they are making approximations of their real-world observations. Even when you put data into a computer uses floating point data to represent numbers, and floating point data necessarily rounds up to a certain number of decimal points, albeit a very large number of decimal points. So the point here is that in the real world, numbers are not always on the nose accurate, and this fact can render many systems that are supposed to be consistent inconsistent. So I just have an example here to illustrate the point. I have the data of some system represented with floating point numbers. I row reduce the system, and what did I get here? I got an inconsistent system. So this kind of thing happens all the time. In fact, whenever I talk to one of my friends who's in some department that's not the math department, so if they do like some real like hard science, the question they have for me is like, well, when have you ever encountered a consistent system? So this is something that people care deeply about. And so we have a real problem on our hands. The real problem on our hands is, well, when most people work with data and they work with systems, their systems are inconsistent, what are we supposed to do? And again, what I keep coming back to is the language of the fundamental subspaces. The fundamental issue when we're dealing with an inconsistent system is that we have a coefficient matrix A, and the vector that we're augmenting with, B, is not in the column space of A. It turns out by making this observation, we allow ourselves to think about the next best thing to solving something. Because of course, if we're working with an inconsistent system, we'll never find a solution. So what we want to do is find the next best thing to a solution.